Hello everyone, my name is Dr. Harry Farwaha. I am the new Chemistry 154 Beat Your Course exam instructor. And just to give you a brief introduction about myself, I have a Master's and a PhD in Pure and Applied Chemistry, many years of postdoctoral experience, and many more years in education for chemistry undergraduate students, teaching at all levels of undergraduate levels, just to make sure that students are fully prepared for their assignments, tests, exams, and even beyond. My main strategy for helping students do well in their exams is to break down difficult concepts and trick questions, and to allow you to feel more able, more confident, and more prepared for your upcoming exam. And today I want to provide you with a sample of our upcoming Chem 154 final exam crash course by going over chemical kinetics. So our upcoming crash course will be a 12-hour crash course, and this is really a little sample of what's to come in that. So chemical kinetics, this is basically the study of the rate of chemical reactions. Well, thermodynamics can tell us which reactions are possible. I always like to say that thermodynamics tells us if. Chemical kinetics is more concerned about when. When will the reaction be finished? And one of the most famous examples of this is carbon in the form of diamond turning into carbon in the form of graphite. Now, we should be aware of the fact that graphite is a lot more disordered. It's a lot more favourable. It has a much higher entropy than carbon in the form of diamond has. So it would tend to be reasonable to suggest that if it's spontaneous, in terms of delta G, that you'd expect the reaction to proceed very favourably. However, it does not. The chemical kinetics will not allow for this, despite the thermodynamic favourability of this reaction. So that's one of the key things to know about chemical kinetics. They can actually compete with thermodynamics. There are many types of chemical reactions concerning chemical kinetics. The one that we're most concerned with are elementary reactions, and as the name suggests, these are stepwise, simple interactions that are occurring in a chemical system. And essentially, they're just two reactants that can combine in one step, or many reactants, as long as it's just one step in the reaction process. So you can have up to 10 different steps in a reaction, and those would be comprised of 10 elementary reactions. So you can have 2A and B combining to give you C. You can see this is spelt wrongly here. I'll fix that later. You can also have A and A giving you X, and X and B giving you C. Now, the overall reaction is composed of two elementary reactions, so you can look at this and view X as being a kind of intermediate that isn't shown in your overall reaction. So just to highlight that, you have an X here and an X here, and those are just intermediates. So let me just get rid of this. So hopefully that starts off in a very kind of simple manner. And we need to go into more detail about what elementary reactions are and how they're used for chemical kinetics. They can be classified based on how many molecules actually have to collide. Now, bear in mind, two molecules are flying around in space, for example, if it's a gas. They have to find each other, and once they find each other, they have to attack each other. And they have to attack each other at the right angle, with the right activation energy, in the right way. And they have to be reactive enough with one another. So that's a lot of considerations. In addition to that, it doesn't have to just be two molecules that interact. It can be three molecules that come in all together. Or it could be one molecule that simply breaks apart. So you have some compounds, especially like explosives, and they actually just fly apart without reacting with anything else. So we can very neatly organize this into three different types: unimolecular reactions, bimolecular reactions, and termolecular reactions. And as I've shown, unimolecular, all it means is that you have one thing before your reaction arrow. So there's only one thing here, one thing reacting. And essentially it decomposes. Unimolecular reactions are commonly synonymous with decomposition reactions. And they can break apart into two things or one thing. That's actually irrelevant. It doesn't matter how many products you form. What matters is how many reactants you have. You can also have bimolecular reactions where you have two reactants interacting. I can just show that in orange. So here you have a bimolecular reaction because you have two things interacting with one another. And last but not least, you can also have molecular reactions, and this is actually the rarest of all, so this is very rare. Because it would take a lot of energy to get three things. Statistically, it would be unfavourable as well to have three things at the right place at the right time to all interact with one another to form C. Now, it's a very rare example, and it probably would only occur in something like advanced biology, perhaps, and maybe that's the only reason that we even have this, where we have a high level of organisation. So this involves a high level... Oh, I'm going to improve that handwriting a little bit. It's a bit messy. A high level of organisation. And that's related to entropy, if you think about it. It's a form of order. You need to have a lot of order created in order to get three things. I'll try high order, actually. Or high level of organisation. So, this essentially, all three things combined, this is under the umbrella of molecularity. So if you're ever asked, what is the molecularity of a reaction, you just need to look at how many reactants are reacting in one step. So that you have to be very clear about that. So really just to clarify that, we have a following reaction. It's a redox reaction between permanganate, between tin 2+, and it's an acidic solution. So we should be aware that this is an acidic solution. Acidic. That's what protons mean. H+ is a proton, and that's synonymous with acidic solutions. Is it an elementary reaction? Well, you have three things that are all going to be reacting. The question is, I can answer this question with another question that we really should have in our mind to help us answer this. Is this all in one step? Now let's probe this. What are the chances that all of these three things are going to be reacting in one step? You have 8 molecules of water forming in this reaction. Now they must come from these atoms over here. So if you think about it, if you have permanganate and you have these protons, I can even show the structure of permanganate. We don't really need to know what it is, but I happen to know, having done chemistry for so long, that it's this type of structure. The negative charge. Now the protons would have to be all around here. So they all would have to be, in order for this to happen in one step, they would have to all be at the right place, and there's 16 of them as well. See, this mechanism is actually more complicated than as I'm showing. This is really just to get an idea of how things would have to be arranged. You have 16 moles of these protons, 5 moles of this and 2 moles of this. That's far too much organisation. So the answer to our question is no. If it's not all in one step, immediately you can say therefore it's not elementary. So you don't even need to look at anything else. You don't need to go into all the detail. All you have to ask yourself is, can it happen in one step? As soon as that answer is no, it's not an elementary step. It's not an elementary reaction. So this was one of the kind of curveballs that they might throw at you. They might give you extra information that isn't actually necessary to answer the question. This was more a philosophical question. So anything with a molecularity of greater than 3 is thought to be impossible. It has not been observed to date. I like to think that it would be observed one day. It would probably be a nanobot machine or something that gets all of these molecules in the right place and they have this tandem reaction going on. It is exceptionally rare though. All of the orbitals, all of the bonds need to break and form in the perfect way. And that would be very rare. So probing into some more mathematics about what reaction rates actually are, reaction rates can be described as a change in concentration over time. Now you don't need to actually do any active differentiation or integration, luckily, for this exam, but you should be aware of what is going on when we talk about this stuff. So we have this expression, V in italics, sorry, and this is the rate of reaction. And it's equal to, it's proportional to a decrease in concentration of A, a decrease in concentration of B. So if I just highlight this, you have negative symbols here. It's a decrease of these reactants. And then you have the positive coefficients for C and D because these are being raised. Another way to look at this, that isn't actually mentioned in here, but I always think it's nice to have a little diagram. you can say that as the concentration of A is decreasing, then the concentration of C is increasing. And you can do the same for B and D as well. So this would be over time. It's a rate, so all rates should really be with the time parameter, and this is the concentration. And that's a nice way of depicting the rate. So you can either view it as the rate of consumption of reactants or the formation of products, and hopefully that's fairly intuitive. And you also have a reciprocal of your coefficient. So you have the small a, small b, small c, and small d, and this is a fixed formula, so you can apply it if you need to. More importantly though, we should be aware of the rate law, and a lot of people do get confused by this. Our rate law is a fundamental relationship between the rate of reaction and the concentration of each species. So V in italics is equal to your rate constant, so K is a rate constant, multiplied by the concentration of A to the power of M, multiplied by the concentration of B to the power of N. M and N are not the stoichiometric coefficients, and I put that in red pen to really highlight this. So M and N have nothing to do with what's in the equation, and we'll cover that in more detail later on, what M and N represent. K is a rate constant, and its value can actually change depending on what M and N actually are. It's temperature dependent, which is no surprise. The faster a reaction goes, generally, the faster the rate. The hotter the reaction, the faster the rate. And it's different for each reaction. So a question I'd like to ask is, why does the rate only depend on the concentration of A and B? Well, the answer is, a lot of reaction rates, if for an irreversible reaction, so this only applies if it's irreversible. Concentration of products do not matter. So if you start to form more products, it's not going to slow down your reaction. So this is irrelevant. And can we figure out M and N from a balanced chemical equation? The answer is no. And we'll cover that in more detail later on. So for now, you just need to always remember, M and N have nothing to do with what's actually written in terms of the balanced chemical equation. So what about the order of reaction? So this is where M and N are really coming into play. So M and N are orders of reaction related to each species, and M plus N is the order overall. So really just to hammer home that point, we can just breeze through some easy examples. Determine the order of reaction of each reactant and the overall order of the following reaction rates, or the following rate laws. So NO, for example, it must have an order of 1, and carbon must have an order of 2. This is simple as just adding this up. So this is a third order reaction. And for this one, it's a first order reaction. You can actually write third and first, because we're talking about orders of reaction. We tend to say first, second, third, fourth, etc. And in this case, you have a rate order of a half, so you don't have to have integer values. And here you have a rate order of 1. So the overall rate order is 1.5. Let me show that clearly. It looks like an S. Good, 5. And for this case, so what do we have here? So if you have a look at this, hopefully, while I'm talking really slowly so that you can hopefully get the same answer I do, the rate order must be 0. You don't have anything to the power of 0 would be 1, and it would be a constant in this case. So it looks like it doesn't depend on any of the species. The rate is fixed, and that can happen in some examples, which we don't need to cover the examples just now, but you should be aware that sometimes in some chemical reactions the concentration won't have any effect whatsoever. We should ask ourselves a question: what actually is the order of reaction? Essentially, it's proportionality. If you double the concentration, what will that do to the rate? If you triple the concentration, what will that do to the rate? Will it double the rate? Will it make the rate go 9 times faster? That's really all the order of reaction tells us. So the order of reaction is the relationship between the concentration, so let's write conc, and the rate. And it might be a linear relationship, or it might be an exponential. So if you times 10 the concentration, that might lead to a times 100 increase in the rate. And hopefully you can see what the order of reaction would have to be for this to work. So, write a general rate law for the following elementary reactions and explain which reactant has a greater effect on the rate if there is more than one. Well, here, the rate, which has the symbol V, must be equal to some constant times the concentration of only your reactant to the power of m. And that's it. That's the rate law for that first example. The second example, the rate will be equal to some constant times the concentration of your bromine radical to the power of m, and another bromine radical to the power of m. You don't need to simplify this. You could. It might, if you have a multiple choice, it might give you the simplified version of this. That would be k br, this is just simple algebra now, 2m, m plus n. So it might give you the simplified version. And again, you don't need to do anything else with that one. So in both those examples, you had kind of the same reactant, either one or two of the same. What about the second example? The rate will equal V, which will equal the some rate constant times the concentration of this methyl cation to the power of m, some unknown m value, times the concentration of hydroxide anions to the power of n. And that's all we need to know. And we're asked to explain which reactant has a greater effect on the rate law. Here we don't have enough information to really know that. And for the last example, rate is equal to V, which is equal to some constant times the concentration of NO to the power of m, and then the concentration of O2 to the power of n. Now notice what I did here. I completely ignored the coefficient, because frankly it doesn't matter. If this has a large value, this could be very large or very small. And I'll put a question mark there because we just simply do not know. I'll just leave it as very large. We don't know. Because if it was, oxygen would have the bigger effect no matter what the coefficient of NO was. So we do not know. So the answer to this, put a little asterisk there, we need to know either m or n. Pseudo first order reaction. So imagine a bimolecular elementary reaction. So you have two reactants clearly, and a good example is an SN2 reaction between BrCH3, so that's bromomethane, and hydroxide. If you treat this as an elementary reaction, we can express the rate law as shown below. So you have two reactants that are reacting together to form two products. One key thing to bear in mind is, what if one thing is in a vast excess? If you look at the change in concentration, if you have hydroxide in vast excess, so really we're zooming in on this key point here. If the bromomethane is swimming in a sea of hydroxide anions, what you're going to do is you're going to have a negligible decrease in the rate of hydroxide. So it looks like hydroxide will not have any impact on the rate anymore. An analogy I like to come up with is if one person is in charge of printing and another person is in charge of stapling, it doesn't matter how fast the first one prints if the second one is really slow at stapling. So it's almost like a rate determining thing. If one thing is basically saturated, if it's doing the best it can, if it's maxed out, the only real thing that's going to affect the rate is whatever is slower. So here we have a much bigger change in concentration, and that's if it's essentially determining all of the parameters that come after it. So the bottom line is, whatever is in vast excess it has a negligible effect because it's maxed out. It can't have any further effect. It will have a negligible decrease in concentration. So this is called a pseudo first order reaction because the concentration of hydroxide was virtually unchanged. So we can take the concentration of hydroxide and call it any given constant. So we can call it K dash and say K dash is the concentration of hydroxide. So it's basically saying, what this is saying is that 9.999 may as well just be 10. And then we can say there's almost no change, so it's almost a constant. So we're saying this is almost a constant. So it's basically negating the difference. So the rate now looks like a first order, and that's why it's called a pseudo first order reaction. Now let's be clear, it's not actually a first order reaction. You do still have a change, no matter how negligible it is, it still exists. And that's why we're calling it pseudo first order. So whenever you see pseudo first order, just think, okay, something's in excess, what is it? Or the other way around, you might get given an exam question, they're like, this thing is in vast excess. Then you would say, well, it must be pseudo first order, or even pseudo second order. As soon as you see the excess, it's synonymous with pseudo. So those are two words that you can lump together for any exam question. Integrated rate laws. Now, first and foremost, when we look at these equations, you do not need to actually carry out integration. So hopefully you will breathe a huge sigh of relief when you're looking at these. However, you should be able to determine what information you can derive from these. And the key to actually knowing what information we can derive from these is to look at the general equation of a straight line, which is y equals mx plus c. And we're asked in our concept clarifier to determine the order of reactions using a straight line plot. So what would we actually plot for this first example over here? So we'll call this example 1. Well, if ln, what I'm going to do is I'm going to rearrange this. We should know our log rule, so I'm going to rearrange equation 1 and say it's ln A take away ln A naught. So we should remember our log rules. If you're dividing two logs, that's the same as subtracting them. And that will be equal to negative kt. This implies that ln A is equal to negative kt plus ln A. In other words, y is equal to mx plus c. So it looks like we always want to have time on our x-axis, and that would be very ideal. So if I were to show that, I can just do a simple sketch of a graph. So it doesn't need to be totally accurate. It's just a sketch. So this is our x-axis and this is our y-axis. And it looks like we have a negative gradient, so I could just show that like this. And it's going to be a straight line. So this initial concentration must be A naught, and this therefore must mean this is your concentration over here, and this must be time with a slope of negative k. So that's all you have to do for that first example. And in the second example, it's the exact same thing. You just rearrange the equation so that you have it in the correct form. As a little hint, I would say that time should really be your x-axis, because you want to see a change in the rate of something. Or it could be 1 over t, as long as there's some parameter of time on the x-axis. That generally is what we normally see. So you can have 1 over a now being equal to kt plus 1 over a naught. Looks like we have a positive gradient in this one, so again y is equal to mx plus c. And if I was to show a graph of this, I'll just stick to the red pen, seeing as it's quite simple. It's going to be a positive gradient, so it must have a positive slope. And this must be k. The slope must be equal to k. So our x-axis must be t again, so it must be time. Oh, let me just get rid of that. Sorry. So this must be time. And this our y-axis must be 1 over a. And the y-intercept, which is what c represents, must be a naught. So hopefully that's clarified it for you. So all this exercise was basically about was asking you to change it into the form y equals mx plus c. And you can argue that's basically just pure math and very little chemistry. It could give you any parameter and you would follow the same rules. Now we need to talk about the half-life. So the half-life of a chemical reaction is the time it takes for half the reactant to be consumed. Now the main thing we need to know here is which equation to use for which situation. If it's a zero order, a first order, or a second order reaction. And we set this up by making A equal to half of A initial. So that's the key thing to note here. So I've actually wrote here half the initial concentration, and I've changed it into words. So these three equations actually come from our three original equations over here. You don't need to go into too much detail, you can just accept that if you try to do the substitution yourself, you would get the same answer. The key thing we need to figure out is how do we answer questions on this? So, we have our question. Americium-241 is a synthetic isotope made in nuclear reactors around the world. Extra information has been given, which we don't really need to know. The first thing I would zoom in on in this question is that you have a first order rate law. So we already know which equation that we're focusing on. And you have a half-life of 432.6 years. What is the rate constant of its decay? Now before I even read the second question, I think I should just focus on the first one. So this is a tactic I like to use when I was doing exams or when I'm telling students how to prepare for exams. There's a certain degree of focus. You should always do things one step at a time. Don't rush it. So the first thing we need to do is get our information to answer the first question. And our information is as follows. The half-life that we were given in our question is equal to 432.6 years. Is there any other information we're given? We don't know what K is. And the second thing you do is you look at your equation. I'm just going to write EQN for equation. And the equation that we're going to use, you have to identify the right one to use. This is how they could trip you up. T to the half, I'm going to use the first order equation, which is the middle one. So this is the equation that I must be using. And it's equal to ln2 divided by K. Then you can simply rearrange this equation and you will get that K is equal to ln2 over T to the half. And ln2 you would just put simply in your calculator and you would get that that's 0.693 divided by 432.6, and that would give you 1.602 times 10 to the negative 3. And that's all you need to know for that one. Now, for the second part of the question, let me just put a little divider there. Now we have some more information. We know what our K is. What else do we know from this question? How much americium would remain of a 25 milligram sample if it were left for 300 years? So it looks like we have an initial value. So we can just call this A0. We can assume it's a concentration and it has the same volume. It won't really matter if it's a solid sample. We can still use the same equation. So that's equal to 25 milligrams, and we can keep the units because the units we're going to end up with is also going to be milligrams. It's asking how much would remain. That must be the A that we don't know. We also have our half-life and we have K. So the equation we need to use, so we know what K is. K is 1.602 times 10 to the negative 3, and T to the power of a half is equal to 432.6 years. And all we need to do is identify the right equation to use, and the equation we can use is the one given in the page before. So again, it's a first order reaction, so here's the equation that must come in very handy. And I would rather show actually this form of it. I think this form over here is the best one to use because it makes it easier to substitute values in there. So I can say that ln A is equal to negative kt plus ln A0. And if you put in all of your values, you will end up with negative 1.602 times 10 to the negative 3 times the number of years, 432.6, plus ln 25. And if you put in all those values, you'll end up with 2.73. So that means our current value of americium must be equal to e to the power of 2.73. So you need to be aware that e to the power of something is the inverse function. If you stick that into a calculator, you'll end up with 15.5 milligrams. Now, this is our final answer, but I want to be very clear on a couple of things. The first thing I want to be clear on is that this is a feasible answer. We started off with 25 milligrams. Now, just because you followed all the procedures, you might want to have some extra reassurance. You might want to double check that you have the right answer. Now, it makes sense if you have 25 milligrams, and if it has the half-life that it has, after 300 years, it won't have reached half its value yet, but it will have gone down substantially. 15.5 is a very reasonable answer starting from 25 milligrams, because after this many years, you would end up having 12.5, half the value. But you're only going 300 years ahead, so it looks like it should be slightly more than half of the value, which is what it is. The second thing we should know is that we didn't change our units. We used years for both the half-life and the years that we were looking for. So these values were the same. So the year stayed constant. And again, milligrams stayed constant as well. So you should always be aware that you're conserving your units. One of the biggest things that they will do in chemical kinetics is they will change units. So you must always make sure that you're a step ahead and that you're being very consistent with the units that you're using. Okay, that's pretty much all I wanted to go through for this little sample, so hopefully this will give you a taste over what I will go through in Chem 154 for the upcoming final exam crash course with Beat Your Course, and I look forward to hopefully seeing you there. Thank you for taking the time. I hope you enjoyed this little mini lecture on chemical kinetics, and hope that you find this and more things useful. One of the key aims I have is to make sure that you know this and everything else you need to know for Chem 1.